Welcome, class. Today we're going to continue our exploration of Chapter 7. So last time I mentioned aqueous solutions as a common form that materials are in when they undergo reaction. So today we're going to focus on aqueous solutions and some of the things that go along with that, and look specifically at precipitation reactions which take place involving aqueous solutions. So let's just introduce a little bit of vocabulary first. So when we're talking about materials dissolving in solution, right, to form these aqueous solutions or dissolving in water, we refer to a compound as soluble if it dissolves, right? So we would say a compound is soluble in a particular liquid if it dissolves in that liquid. So something that dissolves in water, we would say it's soluble in water. If it does not dissolve, we refer to it as insoluble. Now, an aqueous solution, as I've stated before, is simply a homogeneous mixture of a substance with water, right? So something that dissolves, that are soluble in water, and forms a homogeneous mixture. That's an aqueous solution. So a solution is just another term for mixture, right? Or homogeneous mixture specifically. Now, we're going to be looking at specifically ionic compounds and their solubility in water. So when an ionic compound dissolves in water, one of the things we have to understand is that it will break back down into its component ions. It does what we call dissociate. So when I take solid sodium chloride, right, and I dissolve it into water, what's left in the water, that of course we can't see with the naked eye, is the two ions that make up this ionic compound free from each other, right? They're dissociated. So we have sodium positive ions and chloride negative ions floating around in solution. So when an ionic compound dissolves, it dissociates into the component ions. So this becomes important when we think about the reactivity. Now, if it's an ionic compound that contains a polyatomic ion, such as nitrate here, it's important to understand that those polyatomic ions will stay intact when they dissolve. So if I dissolve silver nitrate into water, I end up with silver positive ions and nitrate negative ions floating around. So those polyatomic ions stay together when we dissolve them, right? So they behave just like as they were an atomic ion. And so we're going to look a little bit at these effects here, or some of the properties that go along with this. But, I've showed you two examples here of ionic compounds that dissolve in water. But of course, not all ionic compounds do dissolve in water. There are some of them that don't. So, for example, if I were to put silver chloride into water, so AgCl, it just sits there, right? It sits as a solid on the bottom. It does not dissolve. It is insoluble. So, how do we know what ionic compounds are going to dissolve in water and be soluble, and what ionic compounds are not going to dissolve, are insoluble in water? Well, we have a set of rules, right? These are called ionic compound solubility rules, or just simply solubility rules. And we can see them here listed in our table. Now, I mentioned right up front, you do not need to memorize these, right? You will have access to these when you need to use them, either from your book when you're doing homework and so forth, or on the test you'll have access to these tables. So the way this is written out is we have two parts of the table. We have the first part of the table, which lists ions if they're part of an ionic compound, will make it dissolve in most cases. And on the bottom, we have ions that when they're involved in an ionic compound, they'll make that compound insoluble most of the time. So let's kind of look through these rules. So if an ionic compound has one of these four positive ions, lithium ions, sodium ions, potassium ions, or ammonium ions, then it will always be soluble. Now again, we only have to worry about one of the ions, right? We don't have to necessarily worry about both of them. And what you'll see is that most of the rules in this table deal with the negative ion, not the positive ion, right? The first rule is the only one that looks at these four positive ions that will make a compound dissolve in water or soluble in water. So with the second rule, right, we have nitrate and acetate. So if a compound contains those ions, it's going to dissolve. Now, next we get to compounds that will most often make a compound soluble. So for example, if a compound has a chloride, a bromide, or an iodide ion, it will typically be soluble unless the positive ion is silver, as we saw in the previous example with silver chloride, this mercury ion, or lead, right? So silver and lead are the two most common examples where we'll see where they'll be matched with one of these ions and therefore be insoluble. And lastly, we have sulfate ions, which will make a compound soluble unless the positive ion is calcium, strontium, barium, the alkali earth metals, the lower alkali earth metals, or, of course, lead here. Lead compounds do not tend to be very soluble. Okay, so those are ions that tend to make materials soluble. Now we have some compounds that tend to make compounds insoluble. So we have hydroxide ions, we have sulfide ions. These are going to be insoluble unless, of course, they are paired with one of the positive ions that are always soluble. And then there are a few other examples that make sulfide soluble, right, if it's paired with the alkali earth metals. And then, of course, lastly, we have carbonate and phosphate, which are going to be soluble unless they're paired with one of the four positive ions that are always soluble, right? So these four ions tend to make most materials, most ionic compounds, be insoluble if they're part of them, except with some of these exceptions. So the bottom line is you need to know how to read this table, right? As I said, you don't need to memorize it. You'll have access to it, but you do need to know how to read it. Okay. So let's look at these aqueous solutions and look at some of their unique properties. So one of the unique properties with aqueous solutions that contain ionic compounds dissolved in them, right, is that we know they have these dissolved ions. So a solution that contains dissolved ions are called electrolytes, right? So when you have these ions floating around in solution, they create what we call electrolytes, or sometimes we just call them strong electrolytes. Now, what does that mean? Well, an electrolyte solution will conduct electricity. So if I take a solution that has dissolved ions, or an electrolyte solution, and I put in this apparatus where we're passing current through it, right, it will conduct the current, right? So we'll complete this circuit here so that we light up the light bulb, right? So the electrons will flow out of the battery through the solution and complete the circuit and light the light bulb. If we have pure water, right, with no ions, then it will not conduct electricity, right? And so the light bulb will stay off. So one of the properties of these electrolyte solutions, or these solutions that have ions dissolved in them, is that they will be conductors of electricity. And so we'll often refer to these as electrolyte solutions. Now, the one specific example that we're going to look at where we're doing chemistry with these aqueous solutions is called a precipitation reaction. So precipitation reactions are reactions that form a solid when the two components are mixed, right? So specifically, we call this solid a precipitate, right? So we have these two reactants, these two aqueous solutions, we mix them together and they form a solid. That solid is called a precipitate, and these are called precipitation reactions. Remember, forming a solid is one sign of a chemical reaction that we talked about a little bit earlier. So a specific example here, right, is we have potassium iodide, lead and lead nitrate interacting to form lead iodide and potassium nitrate. Now, the important thing to point out here is the lead iodide, right? So if we were to take and look at lead iodine with our solubility rules, remember we would see that if you have an I- ion, right, the iodide ion, it's going to be soluble unless you're paired with silver +1 or lead +2, right? Well, we have lead +2 here, and so we have an insoluble compound, or something that forms a solid during this reaction. Notice there is another product you could write, this potassium nitrate, but that's a soluble compound, so it's still going to exist as the ions. It's still going to be dissolved in solution. Now, this type of reaction is called a double displacement, and we'll look at what specifically that means a little bit later on. But right now we'll talk about how to use this pattern, this double displacement pattern, to predict these kinds of precipitation reactions. Now, before we look at an example of a precipitation reaction, I will point out that just because we mix two aqueous solutions doesn't mean that a reaction is going to take place or a precipitate will form, right? So they don't always occur. So if the products that could be formed are all soluble, none of them are insoluble, right? Then no precipitation is going to occur, and we just simply would have no reaction. Right? So to keep that in mind as we're going through the process, that just because we do this doesn't mean a precipitate will always form. So let's analyze how we do this. So if we go back to the reaction we were looking at before, how did we know what was going to happen? How can we know what's going to happen? Well, if we take our two solutions of potassium iodide and lead nitrate, we have to understand is when they're aqueous, and that's the key here, that they exist as the individual ions, right? They're dissociated. So we have potassium ions and we have iodide ions, and in our lead nitrate we have nitrate ions and we have lead 2+ ions, right? Now, how do we know these charges? Well, we look at our compounds, and by the formula we know, right? Or we know by where they are in the periodic table, right? For most things. And so if we look at lead nitrate here, for example, right? We know that nitrate, because we know that polyatomic ion is a -1 charge, so that means the one lead paired with two nitrates means this has to be lead +2 to make this neutral, right? So we can know the charges of these ions by looking at the formulas and using what we've learned previously in terms of the common ion charges, what the polyatomic ions are, etc., to predict the charges for what these ions are in solution. So once we know what the ions are, then we can start to think about what's going to happen. So when I mix these two solutions together. Now all of a sudden, I have 4 ions all in the same solution. And these ions are going to be encountering each other. Now, so that we can have different combinations of these ions besides what we started with. Now, we have to understand that only positive and negative ions will come together. Right? So an ionic compound is going to always have a positive and negative. So you're not going to put both positive ions together, both negative ions together as potential products. So if we go to predict our products, we do the opposite pairing, right? So we already have, right, the pairs we saw, and we know they're soluble because we had them at the reactants. So we want to look at the opposite combination. So we want to pair potassium, right, with nitrate, and we want to pair lead with iodide as our potential precipitates, right, our potential products. So if we do that, being careful to make sure that we get the formula right, remember these have to be neutral, right? So potassium is positive 1, it's going to combine with 1 nitrate, negative 1, to give you KNO3. And we have PbI2, right? Pb is a +2, I is -1, so we need 2 of them. So we want to make sure we write these in the correct formula. So now we have our potential products. This is where the solubility rules come into play. So now we need to take these potential products, look at our solubility rules, and see whether they're going to precipitate or not. So let's scroll back to our solubility rules and look at these. So we had KNO3 and PbI2. So if I look at my ions, so I have potassium ions here. Well, I know from the first rule that if it pertains potassium, it's going to be soluble. So I know this is going to be soluble. It's going to be aqueous. So what about lead iodide? Well, we have a rule for I- right here. So we have I-. So it's going to be soluble unless it's paired with silver, this mercury, or lead 2+. So right there we see that this compound is going to be insoluble because the iodine is paired with lead 2. So that gives me PbI2 is going to be a solid, or it's going to be insoluble. So if I go back to my reaction here, I checked my solubility rules and I determined that KNO3 is soluble, but PbI2 is insoluble. Therefore, PbI2 is going to be a solid precipitate, right? It's going to be the reaction taking place, or the formation of this solid. So we would write out our reaction as this. Now, of course, once we write this out, we have to make sure it's balanced. So to balance it, we would have to have the coefficients in front of Ki and KNO3 to give us the balanced equation. Okay, so that's the process. So let's look at one more example here, run through it. So let's say we're given the reaction of AgNO3, silver nitrate, and NaCl, sodium chloride. And we want to write the equation for the precipitation reaction that occurs, if any does, when solutions of silver nitrate and sodium chloride are mixed. So we're going to do the same thing. We're going to look at and say, okay, when these are aqueous, what ions are present? Well, if I look at this formula, we have Ag+1, right? Because I know NO3 is the -1, so we have Ag+1 and NO3 -1. Of course, we have sodium +1 and Cl -1. So we have our ions here. So now we're going to swap them, right? So we're going to pair the silver with the other negative ion, the chlorine, and we're going to pair the sodium with the nitrate, and we're going to come up with potential products. So for silver, we have the silver, it's a positive one, the chlorine's a minus one. So we're going to be AgCl, there's the formula. And the sodium and the nitrate, we have sodium, it's a positive one, so it's compared with 1 nitrate, NO3. So these are going to be my two products. So I have silver chloride, and I have sodium nitrate. So again, now is when I need to consult my solubility rules to see whether I actually have a reaction, if I form a precipitate. So let's go back again, look at our solubility rules, and we have silver chloride and sodium nitrate. So if I look at silver chloride, I have a rule for chloride here, and it says it's soluble unless paired with silver positive 1. Oh, okay, so that tells me right there that it's going to be insoluble. Now, we have to always check because they could be two precipitates. So we have sodium nitrate, but the more you do this, you realize, oh, it's sodium. Anything with sodium is going to be soluble. So now we have our results here, and the silver chloride is our precipitate. The sodium nitrate stays aqueous, and so now we have our reaction. Last thing is to check to see if it's balanced, and so we have silver, 1 on each side. We have nitrate, 1 on each side. Sodium, 1 on each side. Chlorine, 1 on each side. So everything's balanced with a coefficient of 1. So this would be our final balanced chemical equation. Okay, so now we've learned a little bit more about aqueous solutions and what that means, and specifically how ionic compounds behave when they dissolve in water, and how to go about analyzing a precipitation reaction using our solubility rules. Next time, we're going to look at one more kind of reaction in the next lecture, and that's these redox reactions, specifically combustion reactions.